All right. Hello, everyone.
Good.
Mike, can you hear me through the mic? All right. Not on? Okay. Can you? All right. All right, great. Well, welcome, everyone. Welcome to I believe, the last colloquium, EECS colloquium of this semester. It's our great pleasure to be hosting John Martinis from Qolab and UC Santa Barbara, from where he very recently retired. John Martinis is not a stranger to Berkeley. He did his PhD here at the physics department with John Clark. This was back in 1980s, where already they were looking at effects of quantization on electrical circuits and observing macroscopic quantum mechanical phenomena. All right, this was 1980s, and since then, he's been continuing to pioneer the field, advance quantum computation with superconducting circuits. After his PhD, he's worked on a variety of low-temperature device physics during his career, including work he did at NIST. And since the 1990s, he's been focusing on quantum computation. He received many awards. He was awarded the London Prize in Low Temperature Physics in 2014 for his work in this field. And after his work at NIST, he started a group at the physics department at UC Santa Barbara, somewhere around mid-2000s. And in his group, he was able to advance superconducting qubits to a level where they could show that the gate errors in superconducting qubits are below error correction thresholds. So this was an important moment. It was a proof of principle that was, I believe, enough to convince Google that, well, maybe we could build these things. And he launched the quantum computing effort at Google around 2014. From 2014 to 2020, he worked at Google to build a useful quantum computer. And this work culminated in the demonstration of quantum supremacy experiment in 2019. He was awarded the John Stewart Bell Prize in 2021. This is all very fascinating, but John thinks that the pace was still not enough. We still need to go faster in terms of advancing quantum computer. And that's what his new startup, Qolab, is about, and I believe that's what he's going to talk about today. With that, it's my pleasure to introduce John.
Thank you. Thanks for everyone coming out and listening. There's a lot of progress going on in the field of quantum computing. Even this week, Google had a nice publication of a new surface code experiment that advanced the field. Lots of other things going on. And this is great. But what we're going to talk about today is what do we have to do to take it from still kind of a scientific endeavor to make it useful and make it practical. And I want to talk a little bit about our business and engineering ideas we have, although there's still a lot of physics, and talk about how we think we could make these quantum computers much better and why we're kind of doing it the way we're doing it. So for some of the new students here, I'll give an introduction. Sorry, it's really fast, but I want to get into kind of the strategy, about kind of the business case of what we're doing, the engineering case, and then I'll talk about some of our new ideas on how we think it is to scale up a quantum computer. So for the new students, what are we doing here? We can store and manipulate information with quantum states. And with the laws of quantum mechanics allow you to be in a superposition. So if you abstract that to let's say a bit 0 and 1, in a qubit, you can be in a superposition of 0 and 1 at the same time, like you can do with wave functions for the hydrogen atom. What this allows you to do in the end, conceptually, is to do a kind of parallel processing where you can put this 0 and 1 state, run it through your quantum computer, and get this kind of parallelization of the computing for what happens to 0 and what happens to 1 at the same time. Now, okay, 1 qubit, factor of 2, who cares? If you had 2 qubits, you now have 4 possible states. You've just doubled the number of parallel processing that you can do by adding 1 qubit. 3 qubits, you have 8 states, 4 qubits, you have 16, so that you're exponentially growing the amount of processing that you're doing. And by the time you get to n equal 50 or so, 2 to the 50 is the amount of processing kind of equivalent to a supercomputer. That was the quantum supremacy experiment. And by the time you get to 300, 2 to the 300 is more states than there are in the universe. So obviously you're doing something interesting. Now the big problem with this, although you get this parallel computation, quantum mechanics says you have to do a measurement at the end. And when you do a measurement, you kind of collapse the amount of information that you've been processing. So now you only get 50 or 300 bits of information. And the hard part about quantum computing is coming up with algorithms so that you run the algorithm and then you do a measurement at the end, and from that minimal amount of information, you can then get something important. And you know, an example of this is the Shor factoring algorithm, where you know, the end answer is more or less what the factors are, at least a good percentage of the time. Now, I'm going to talk about hardware here, and we're going to talk about superconducting qubits, which is just, it's in electrical circuits where you see that the currents and voltages obey the laws of quantum mechanics. So here we have a big ground plane, which is in the light brown, and cuts in the ground plane, which are a dark brown. And this cross here forms a capacitance. And these tunnel junctions that are down here are overlapping metal with aluminum oxide. It's called a superconducting Josephson junction. And that forms a nonlinear inductor. So you're basically just making a qubit out of an LC oscillator. By being nonlinear, you can then see the qubit behavior. And then the zero state is if there's no energy in the system, and you can draw a wave function like that, as you studied from, let's say, harmonic oscillator quantum mechanics. And for the one state is with 1 photon of energy in the system, you could think about the wave function given something like that. And by putting in microwave pulses through the control lines, you can push on this qubit and make transitions between 0 and 1. And you can also change the frequency of this qubit, put by magnetic flux in here to do some phase changes in the device and other control. But it's really, when you think about how this works, it's about 60% RF microwave engineering, okay, which is something, you know, you may know a little bit about. And you have to put in quantum mechanics too, but a lot of your intuition comes from microwave engineering. This is the quantum supremacy chip that we made at Google. These crosses here are the qubits. These blue boxes are the coupling between 2 qubits that we can turn on and off with some signals coming in. Here's the chip that we're looking at here. The bottom of the chip, you can see the wiring going from inside here to outside bond pads. And then the qubit chip is on top of here, and you put little indium bump bonds to electrically connect these together. So yeah, so this is what was made when I was there. And then you take that chip and you put it into a printed circuit board mount where you wire bond to this, you bring it out to a bunch of connectors, and then that all goes inside of a dilution refrigerator, which is at very low temperature, so that the energy, K Boltzmann times 10 millikelvin, is much less than the quantum of energy at 5 gigahertz, so that your thermal noise doesn't swamp out the device and cause errors in it. This little PCB mount is here. We then come up to a bunch of filters that go up to room temperature and control system. So the experiment we did at Google was a quantum supremacy experiment, was designed to test if quantum mechanics still worked if you do a very powerful computation with a lot of qubits. And the computation here actually became very hard and impossible to kind of reproduce on a classical computer at the largest number of qubits. So basically what we're doing in the algorithm here is we're using this chip to be a random number generator, but it's not quite random. There's some correlations. So we use a classical computer to simulate the circuit and check the output of the quantum computer with the classical and see if it matches. And at very large, small number of qubits, 12 qubits and running about 250 total gates, about 40% of the time it matches really well. But because qubits are naturally fragile, as you go to a larger and larger system, the percentage of the time that it worked out well went down and down exponentially. So that the time we got up to 53, that was about 1% or so. However, to check this, you need to check it with a computer, classical computer. In the beginning, you could do it with your laptop. And then as you got more and more, remember you have this 2 to the n parallelization going on, kind of need a workstation. And by the time you get at the end, you need a data center, and you change a little bit, it's even worse where you can't actually test it perfectly. And you can show that the quantum computer is working properly. In fact, the most important line here is the black line, which is a prediction from simple gated measurement errors and doing the whole quantum computer. It's the red circles, and they match. So it says that there's no new physics going on that can screw up the quantum computer. So this is really important. So at this point, I want to talk about moving forward. Okay, what do we want to do, not just to show for a mathematical problem, for a useful problem, what you need to do. So I'm first going to talk a little bit about engineering and some business metrics of what our plan is. We want quantum utility, and I'm going to say there's probably hundreds of things you have to worry about as a systems engineer, but there are 4 that you really need to focus on. And first of all, you have to have low qubit errors, and those errors have to be pretty small. They were about 0.3, 0.5% in the experiment I told you. We probably want about 10 times better, maybe not so good, but from 3 to 10 times better in order for you to build a system that works properly. You have to have a large number of qubits and scale it up, especially if you want to do quantum error correction. It takes a lot of qubits. So what we're going to talk about here is how to scale up to build 20,000 qubits per wafer module, which is something about this big. Okay, and then how we can tile that together to go even more. So we're going to talk about how we're going to do that. Your qubits have to be have a connectivity. Basically what we did was 1 qubit was connected to its 4 nearest neighbors. That's good enough. It's actually tolerant to some dropouts of the qubits. So it's very, very reasonable here. And finally, this is kind of the subtle one, is the speed. Okay, how fast does it work? Okay, now it's often said that if you have this exponential power of a quantum computer, speed doesn't matter so much. This is not correct, okay? You absolutely need speed. And one of the reasons it's interesting is if you look at superconductors, it's about 50 nanoseconds, maybe a little bit faster to do the various gates you're making. Whereas if you look at, let's say, atomic systems, neutrals or ions, whatever, it's from 2,000 to 10,000, maybe even 100,000 times slower. It's just the atom interactions are slower. Now the problem here is that if you look at utility scale algorithms, you can kind of barely do it with this kind of speed. Okay, so if you go to these other systems, unless people make dramatic improvements in it, it's going to be really hard to get them to do something useful. It might be possible, but you really like the speed. Okay, so that's what we have, is speed needed, but you have a challenging control system problem to deal with. Okay, so we'll talk a little bit about that. Okay, now this is a lot of stuff, don't read it, okay? The important thing here is right now we're maybe at 10 to 100 or 1,000 qubits, and there are things we have to do to improve it. And that's what people are working on. But when you start talking about building 1 million qubits, you have a lot of stuff to do and get right to get there. Okay, and we just addressed some of the things here that you have to start working on. So if you're making good progress now, it doesn't necessarily mean that you can fix all that. And of course, everything you'd have to do now, you have to make upward compatible. So it's really important to think a little bit about the long-term goals of what you're doing. And I'm going to talk a little bit in this talk about how we're going to, scale up and do something like that, because it's not obvious that that's going to work right. I also want to talk a little bit about the business aspect of this, which is kind of interesting. And what happens now is most of the major efforts are what's called, vertical approach. So, it's good for engineers to know about business. And the basic idea is that you have one company that's doing everything. Quantum processors, mount, wiring, fridge, maybe they're buying some of this, control half software. They're doing everything themselves. Okay, and that's good because you don't have to modify a complex supply chain. You can get all the value. You own everything, so you get all the value out of it. But there's a problem with this, and it's very costly to build the stack. You can't use existing, let's say, manufacturing infrastructure from other companies. You have to hire people, and you can't also always hire the best expertise in it. And I'm going to say, I think the physicists are being a little bit naive about how hard it is to build this thing. Okay. Now, just to give you an example here, in the 1950s and 60s and 70s, computers were made by vertically integrated companies. And the best example is IBM. But in the 70s and 80s, it went horizontal. So you had Intel, you had hard drive makers, all these people working on the separate components because they got very complicated, and you had to have these separate business elements to really focus on it. So our approach is to say, yeah, we're eventually going to go horizontal, and we want to use that expertise. So we think it's kind of the right time to do it. I think it's been good so far, but I think we're past the 1970s in terms of the technology. So for example, for our company Qolab, we're the system integrators. And for foundries and tools, we're using applied materials. For design tools, we're working with Synopsys to do things. In electronics, there's a potential we'll collaborate with NVIDIA. And in terms of a supercomputer manufacturer, we're working with HP Enterprise. They built the Cray, and they built supercomputers. So we want to work with this whole lot of number and others to build this. And I'll talk a little bit about that. Okay, so now we get to the most important slide of this talk. Okay, so that's this diagram. Let me explain this diagram. And this really comes with what is our big strategy? So basically, the existing superconducting fab efforts are mostly incremental. It's getting better over time, but it's not too fast. And for example, they use something called shadow evaporation or liftoff to make their junctions. No one in their right mind would develop technology that's based on something that sturdy. And I'm going to say the existing efforts don't really have, in our minds, a clear path to scale to 1 million. It's very aspirational, okay? So this is the problem. Now, let me try to explain it in an approximate way, but I'm just going to say, what is the number of qubits versus time? Okay, and how are we meeting this 1 million qubit rule? So this is UCSB, where we did a first simple error correction, quantum supremacy, and then this is today with the Google effort for this really nice surface code. Now what happened is we had the quantum supremacy experiment. We did a big pitch to Google and said by the end of the decade, we were going to get to a utility scale at 1 million. It was very aggressive, but 10 years, whatever. But if you look at this, it's a little bit flatter than you would like. So do you think it's going to be possible in the next few years to drastically accelerate the growth of the number of qubits and importance. And the nice thing about these experiments is the qubits got better and they did fundamentally important experiments along the way. But do we think that it's going to be this exponential growth that's already on, a log scale? Okay, so you're going to see a double exponent. The other way I like to think about it is if I look at this extrapolation in some way and think about when we'll get to 1 million qubits, I will be dead. No question about it. Okay, and I'm going to say that most of the people working in the field will be retired, if not something else, okay? So, how do we solve this dilemma? I would really like to build a useful quantum computer before I die, before I really retire. Okay. So, is there a miracle technology we can use to do this? And we think the answer is yes. Okay, we just have to use it right. And this is the new approach, is we're going to work with semiconductor fabrication companies, tool makers in specific, applied materials, where we can use their most advanced fabrication right now. It happens to be in 300 millimeter, which is what we need. And we kind of build the proper tools and we focus on making good qubits. And this is what we started. We've working with applied materials for a couple years and really accelerated that in the last 6 months. So that's the basic idea we have here, is because people in the semiconductor fabrication is way better than you can ever do in the academic lab here at and in Corey Hall or even in a small industrial. Certainly something we can't do in Qolab. Now, with this in mind, we can talk a little bit about it, but I want to say that one of our theses here has been getting rid of liftoff, to make the qubits better. So we've actually been working on this this is not in applied materials, this is in the University of Wisconsin, where we've taken this transmon device. Here it's a circle, there's a ground between here and here, and then we make short little junctions between here and here instead of long wires here that is typically seen in this. So we're trying to minimize the size of the liftoff. And basically when we did that earlier in this year, we got much better qubits. And average of those qubits are 100 to 200 microseconds. They're not the best in the world, but they're pretty good. This is 800 microseconds, that's our best. But we really saw some improvement in it. So I want to explain this a little bit more and how we do this. When we look at the qubits, we actually measure the memory retention time. It's called the T1 time of the qubit. How does the energy decay over what time? We measure it versus frequency. So we take our qubit at the maximum frequency of 5.1 gigahertz. We do a 0 to 1 transition, and then we change the flux so that we're at some other frequency, and then we idle this for a certain amount of time, various amounts of time, and then we come back and look at the decay. And when you do that, you get this qubit occupation going from 1 to 0, so it's 1 initially, and then it decays over time. And some places it decays over long times, and some places it decays over short times. This happens to all the qubits. It's not talked about very much, but this is it. And what you tend to do is just bias it, operate it away from these bad points. Now, we want to look at this and understand this. So what we do here, this is actually in Google about 5 years ago with an old chip. We just scan the frequency and measure the T1, which is here from 0 to 42 microseconds. And then we see that there are these holes where it's bad. And then these holes, these frequency where it's bad, drifts in time in some way here. And you can see this and you can understand that in this theory called two-level states. If we do the same thing with our new process, we see a very similar kind of thing, but now it's on a 250 microsecond instead of 50 microsecond scale. So it's significantly better. So we can make better qubits. It can be stable. Things can work well. Now, what I want to do next is talk about what we do is we take, all these times here, and we do a histogram of all those times, okay? So there's some really good ones that are bluish and some that are red, and we just do a histogram of that. And we plot it as an integrated histogram or cumulative distribution versus T1. And for example, this point right here, okay, that's 10 to the minus 1. That means that 90% of the qubits have a higher T1 and 10% has a lower T1 than that figure. That's what it means. Now, the interesting thing is we've looked at the data from Google, which we took 5 years ago. Their data is much better now. And you get typical curves like this. You get a curve from IBM, which we just pulled off of their website. We give them credit for showing that so we could look at it. And you see that this result kind of looks like the Google result, just shifted over and better, which is nice. And then we look at the University of Wisconsin, this new result, which we get the same thing over here. It's a little bit tighter distribution, and these tails are much less. The tail starts maybe 10 times lower and 10 times lower in things. So these tails are significantly better. And we think that's because we're minimizing liftoff as much as possible. And that process is giving us some defects that can really degrade the qubit. The other thing very interesting about this is just if you look these two qubits, which are more or less the same performance in terms of average, this tail, lower tail, actually gives you something like a 2 times lower logical error rate when you put it into a complex algorithm as computed by our theorists. So we think this is really going to be better to improve this. So we want to look at this data very carefully to understand that. Kind of related to this is what happens, yeah.
May I ask a question about the previous plot?
Yeah, go ahead.
So the lifetimes you have there, are those are not for isolated qubits, right? Those are for like...
They're just a single qubit.
Oh, these are all for Google and IBM as well?
Yeah, now, okay, some of them were in a big quantum computer and ours was isolated, so it's not fair.
Okay.
But, okay, fine. It's much harder when you put it into a big package to make everything good. Yes. So we totally agree with that statement. I think mostly what I'm saying is you should be measuring. The real scandal in this field is that everyone quotes their hero best device. And we're somehow have to understand this. And sure, let's quote the median, but I'm also saying let's quote the tails because the tails matter too. And this is not surprising. When you make an engineered product, it's usually your worst devices that cause your whole system to fail. So you really want to understand your worst devices. And that's kind of described in my next slide, where, this is the IBM. You have some width of the T1 and gate fidelities, okay? Now, this is just an illustration of this. This is a yield of some CMOS devices. So let's say these were a bunch of qubits, and the white and yellow is good, and the blue and red are bad. If you're making a 5 or 10 qubit device or 20 qubit device, you choose it from the wafer here, and everything looks great. As soon as you start scaling it up and having to do over the whole wafer, if you don't have your process under control, everything's going to go to hell. So you really want to have reproducibly good devices in order to do that. And again, okay, how do you do that? Well, we think you go to a proper semiconductor fabrication. Another example is when you deposit the metals on this to make these particular structures, you have two-level states, you have amorphous materials that can give you loss. And it's really important to know what the interface is between your metal and your substrate. And you want to have that as small as possible in order to get the best devices. Now, what we do in applied materials is we have an in situ cleaning where you can get an atomic interface between the silicon and the aluminum. And to do that and process that in all vacuum, so that's maximally clean. So that's one of the things we're working on with them. Here's another device. We talk about getting rid of the liftoff junctions. And here is a very preliminary result of making liftoff junctions, where these are the two electrodes here. This is a small little 0.2 micron junction here. And then we have the counter electrode going here. And here you can see that that counter electrode has a vacuum underneath it. So that way we get rid of any SiO2 or something that is going to give you loss. So this, it doesn't give good qubits yet, but we've been able to do it. There's a lot still yet left to optimize there. So yeah, we're working on doing that, and we'll see how good we can make that. Okay. So now we come to the second most, this is maybe the most important slide, is how are we going to scale up this to thousands to millions of qubits? So this, I'll explain that very simply here. This is very much motivated or inspired, I guess you can say, is by Cerebras making a AI processor from a 300 millimeter wafer, the entire processor. And there's a lot of tricks that go into that to make sure that you can yield a big processor, even though there can be defects in it. We're going to do a similar processor, but our defect density of these qubit devices is way smaller, way less important. So the basic idea here is we're going to have a 14 centimeter by 14 centimeter blue die here that has the qubits. And then we're going to bump on that to a wiring wafer, again made on a 300 millimeter. So it's a big bump on. And that this will bring the wiring from the qubits, 20,000 qubits. You'll bring out about 100,000 wires from 20 millikelvin to 3 Kelvin. Okay, and then here you're going to do some micromachining so that you can get rid of the heat load going down here. And with 1 micron pitch, you can easily get 100,000 wires and do all this. And then at 3 Kelvin, you have circuit boards made out of flex with maybe chips, control chips, either at 3 Kelvin or at higher temperature, that go in and control all this. Okay, and what's nice here is that you think of this module electrically as a 3 Kelvin module, but of course you have to cool part of it down thermally with the dilution refrigerator and the like. But at least you don't have to worry about the crazy wiring, okay? And the nice thing here is these are superconducting wires, so they can be a micron or half a micron wide and be a perfectly good transmission line. Can't do that with normal metal. So you use the property of superconductors to do that. And then, that's one module, 20,000 qubits. You then would maybe tile these together. You'd have some kind of capacitive coupling between here to make a bigger chip and to do the communication.
But when they go into the CMOS, they're not Q anymore.
Excuse me?
They're not qubits anymore so now you sort of parallelize them on the classical level. You have
The CMOS here is control chips for putting down the microwaves and the pulses we need.
But how do you connect two of these things together that they still connect?
So these CMOSs, or this CMOS is a series of stacked things, and then you take this module and and stack them. This is rotated 9 degrees. You then stack them together, is the idea.
And how do you connect them?
Connect what?
But you still want to have information flowing from one.
So you have the CMOS. You have spring fingers here, dense arranged spring fingers, which you can buy. It then goes to the wires here, which then goes down here and go through the bumps to the qubits. bump bonds, spring fingers, 100,000, which you can make. I found a company that can make that. Now, of course, we have to get it all to work. We have to make sure that this radiation isn't contaminating. There's a lot of things to get here. But the idea is you can make a module that you can test and make sure it works right, and then you take those modules and put it together and make it even bigger. That's the idea. Okay. So that's what we're doing. Now, when you do this, this solves the wiring problem, but it doesn't solve another problem, and that's the problem of measurement of the qubits. And what typically you do is do the measurements. You have a measure line. It goes through a circulator that's about that big, and then goes to another amplifier, which again is that big and has high power. And it's just a real mess, and you have a lot of components. What happened is one of our co-founders, Robert McDermott, has built circuits where you basically build a phase qubit, a type of phase qubit that does a measurement, and then you read it out with a squid amplifier at 3 Kelvin, where all of this can be integrated onto the wiring wafer. And, again, we have to show we can scale it up. But this is from the paper, which was made 2021, a few years ago, where the measurement errors are pretty low. We'd like to make them a little bit lower. This is only the first try, and we think we can do that. So there's a way to scale up and integrate this very complex measurement circuit with doing something like that. And that's as key as anything else. There's no sense of doing this unless you can do both of these things. Okay? I just want to show that we're working with Fermilab, and we're making Cryo-CMOS, and this Cryo-CMOS can be used to bias up the squid, which is at 3 Kelvin, also do some other kind of biasing and control, which shows that they can make a 6 or 8-bit DAC that works well at 3 Kelvin, and this can work with the supply voltage as low as 50 millivolts. You're talking something about 100 microwatts of power. So this is good too, because you have to even minimize your power at 3 Kelvin. So that's the basic hardware. There's other things we talk about. I just want to talk about the collaboration a little bit. One of the things we're collaborating with Synopsys, and we're working with them to look at electromagnetic simulators. Now, right now, if you want to design these circuits, there's very nice software out there where you can draw up your circuit. Here's a transmon, here's a readout. You could figure out all your parameters, which then goes into a simple circuit model, and you use quantum mechanics, and you can figure it out. And you can do that up to a few qubits. The problem is we want to make 1,000 or 10,000 qubits on this module. Is this going to work? Now, we think this kind of quantization will work properly, but the real problem is microwave crosstalk. You have these qubits that are next to each other, and you really want, if you drive one qubit, the effect of the qubit next to it to be like 10 to the minus 4, very, very small. If you use think about standard microwave engineering, a crosstalk of 10%, maybe 1%, gonna be okay, but we want 10 to the minus 4. So we really have to learn how to do this better. And right now, the problem is if you try to just mesh this with more and more meshing, it just gets too big of a problem. So we want to work with Synopsys, and they basically have something called domain decomposition, which we think we should work, which is what they're doing right now for phased array antennas. So this is a picture of a bunch of antennas that are phased array, and this is the radiation pattern coming out of it. And what you can do with domain decomposition is take all of these and simulate them, but also simulate what happens when you get connected so that you can do a proper full simulation. And the most important thing is you can put this on a big GPU cluster to break it up so that you can do the, simulate all these domains and the connections properly. So we're going to work on that, and we hope that that can be something available to the field, because this is a real problem that has to be fixed. Very practical engineering problem. It's purely classical electromagnetic simulation. And then we're also working with quantum machines, and they have a control system. They also have a decoder that's made with NVIDIA. And the idea here is you can take and do a simulation where you take from a computer and preload or stream in some syndromes, the measurements that you make on a quantum computer when you're looking at a surface code quantum computing, for example. You say what those are, and then these get passed to a big NVIDIA GPU, CPU, and you can test whether the surface code decoding is going to work real time. So you don't have to build a quantum computer to start testing it. And that's what they're working on right now. And in fact, it's quite good. The data stream between this looks fine. They're still working on whether they can decode fast enough. But these are things that people can do right now. So I've given you kind of a flash view of what we're doing. If you want any details, we have a paper on archive. Here's the author list. We have Hewlett-Packard labs, 1QBit, quantum machines, University of Wisconsin, and Fermilab, Applied Materials, and Synopsys. So we have a large number of collaborators. They're working on the stack from the very bottom of the baking to fabrication all the way up to algorithms and error correction. And we're trying to understand this in a very concrete systems engineering way. And obviously there's going to be a lot more work, and we're actively encouraging people to give us feedback, tell us what's wrong so we know how to make it better. But it's a very serious effort by this group to figure out how to do this. So just for summarize here, there's a lot of hardware and software challenges. I'm going to say are now unresolved or overlooked by the existing efforts. I mean, it's good that everyone's working on it, and it's fine, but what we tried to do here is to start addressing those issues, at least point out what we have to work on. And we think the biggest thing is we're going to leverage the semiconductor fabrication to do this. And, we've given some resource and sensitivity analysis. We have this nice consortium working on it. And, this position paper, we hope, kind of outlines what we want to do here. So we're looking for people who might want to collaborate, Q with collaborate, quantum collaborate. And if you're interested, let us know. Okay, thank you very much.
All right, thank you for the very exciting talk. We have time for questions. Jeff.
Let me ask about that applied materials.
Jeff.
Let me ask about that applied materials cluster tool that you showed. Normally, the business strategy for applied materials to develop a machine like that is that it enables high volume so that there can be a business case for them. How do they look at this business and justify putting the engineering in to design a new cluster tool for this?
Yeah, so the business case is very interesting. So let me tell you what the big problem is. The big problem is if you try to buy that tool yourself, your Google, which has a ton of money, $100 million is way too much for a process you don't know that'll work. Okay, you go to IMAC, which has a superconducting thing. They want to shoehorn their process into their CMOS tools because no one can afford this. So how do you use the most modern tools and you can't afford $100 million? Okay, and fortunately we were able to convince Applied Materials that they could take an existing cluster tool that, they're decommissioning or not using or whatever, put in a few tools for us, and then try this out. And then if it works, they're hoping there will be a big need for it. Or maybe they, build the qubits themselves of a smaller volume. Okay, so that's maybe an option for them. But yeah, this was the big problem that we started with, and so in fact, the really hard part to get these people interested is to sell them that you have an idea on how to make the qubits better using their tools than whatever. Not just, we're going to sputter niobium and aluminum, lift off, whatever. We had to come up with a process where they saw that they could do it better. So that's what we did. We have a lot of other things that we thought about too. And then working with them, we worked with them for 2 years, kind of showing that we weren't, flakes, okay? And to show that we had good ideas, and then we were doing. Now, we have to pay for, use of the AMAT materials, but they're obviously kicking in money too. But it's relatively inexpensive to do once you convince them, that this is interesting. And they're working with other quantum computing companies now to do this. And I really appreciate them being forward that way.
Other questions? Yes.
Thanks for the talk. I think at some point you mentioned you had 20,000 lines going from your CMOS cryo control to 100,000 qubits. Does that include qubit control?
Well, it's more like 100,000.
100,000 lines for 100,000 qubits?
Yeah, something like that.
Okay.
Now, we do have a way where we might be able to reduce that number. Mm-hmm. Okay, but initially we're talking about just brute force it. And there's a reason why, look, we would love if you can reduce the number of wires, okay? But the problem is, there's usually a trade-off. If you do some kind of multiplexing to reduce the number of wires, you're not so optimally controlling the qubits. And qubit errors are everything. And if your qubits errors are higher, you're going to need more qubits to do a control. So, our zeroth order plan is to just, kind of brute force it, to have full control, know what you're doing. And I think if we can make everything reliable enough, there are multiplexing schemes where we can bring down that number, in a reasonable way. Let's say in the way that the neutral atoms are doing. We think it might be possible. So, but you have to show that that's possible first. And we definitely have to make our qubits better to do the baseline or to do anything more sophisticated. There was a question over here.
Okay, I'm looking for students first.
Oh, yeah. Students get priority, yes.
Okay.
Sure. Throwing
Bro.
They're good at catching.
Yeah, so, you talk about, scaling the superconductors to 300 nanometers, and then you're, using quantum machines, NVIDIA. I feel like, that's a lot of stuff, and it could probably cause to me, it sounds like it could cause a lot of, compatibility issues. But, I'm just an undergrad, so I don't know a lot about, the quantum computing scene. But what makes you think that, it's time to sort of branch out horizontally rather than keeping it vertical?
Yeah, that's a good. So first of all, we have a lot to prove and a lot to show. And, we're clearly being optimistic that we can solve the problems. When I look at it, it looks like these problems can be solved given the right amount of money and time to do it. But yes, this is very hard. What I would say is, why do we want to go horizontally? I'm going to say that I moved from UCSB to Google in 2014 when we got enough stuff going on at UCSB where I thought we could scale up and build it. Because frankly, in UCSB, the experiments worked better than I thought. Like the first time in my professional career. And then when we went to Google and we were able to put resources to solve it and do the bump bonding and everything, we were really able to scale up in 5 years, from an academic level to that. And then, I left Google. It got a little bit too academic for me. But as I left and started rethinking what do we need to do, we came up with these ideas on what to do. And then the CEO, Alan Ho, mentioned, well, we're doing this. This is really doing a horizontal integration. And that's the way the semiconductor industry, really flourished. So it was kind of an evolution of ideas and then realization, of how to do things. But it's just the thesis, and until you try it, you don't know if that's going to work. But what I would say is when we've worked with applied materials to try to solve our fab problems, we're in a different universe than we were before. It is unbelievable what they know how to do. And, given that and other kind of interactions, we think it's really time. And it's because we know enough physics and we've done enough to do that. And the cost to do this is not, with applied materials chipping in the right way, is reasonable. One of the things that it was very interesting is I hear a lot of times people say that making silicon qubits and making a quantum computer with silicon qubits is going to be a better way to scale up. My experience with looking at some proposals and whatever is that it's not as favorable. There's certain advantages, but there's certain disadvantages of doing it that way. That we have to see if it's going to actually pan out. But there was definitely a path forward here. We just have to get things to work in a couple of years.
And last question. All right.
I could talk to people afterwards.
Yeah, so for extra questions, we can continue here.
But it's only 5. So I guess you have to stop at 5?
Yeah, okay, I'll do two questions since you sound willing to stay. All right, Eli.
Hey, you're tough here.
It was, you pointed out, it was a great achievement of quantum error correction just happened in the past year at Google. But we had enough qubits back in 2014, even earlier. We had enough qubits to demonstrate quantum error correction. But it only happened this past 12 months. So I'm worried that there are some decoherence mechanisms that have not been identified, that are very subtle, that do not follow an exponential decay, that happen at early times. Very hard to. So what's your explanation why it took so long to demonstrate quantum error correction?
So they demonstrated break even a couple of years ago, but it's taken them basically 5 years to figure out what their decoherence mechanism was. Okay. Now, if I would have stayed at Google, it would have not taken 5 years.
Okay, I think this is a natural ending point. So,
Is that a good way to end it?
I think that's excellent.
I was trying to figure out how to be diplomatic.
No.
Thank you for laughing.
Perfect, and way to end. If you want to discuss further, please come here. And let's thank John again for an excellent talk.